Good morning, I'm Cody Hendrickson. Today we're going to be looking at how to do C++ singly linked lists. Let's go ahead and get started. Now we've been developing with our list node structure for the last few weeks, and if we take a look at that, we have our structure here, how we started off with the node object. Inheriting from node, we have our array node, which adds to that the idea of a next pointer, and we saw that implemented with our CTEC list and our CTEC array. And we're going to take a closer look today at the CTEC list. And so we take a look at the detailed UML for this. We see that we have our data member section. We have 3 data members of size, head, and end. And then we have a bunch of constructors and methods that we have attached to this. And we have basically grouped together in the idea of the get, the add, the remove, and having a set as well. And so we're going to take a look at those in a little more detail as we go through this. First thing we want to do is look at the actual structure of our list. When we look at a linked list, we have 3 main components to the actual list itself that we have to keep track of for the C++ list. The first one is our pointer head. Then we have our pointer to the end, and finally our data member for size. Those are the 3 components that actually make up the idea of this. Head and end will go into a lot more detail, but size is obviously the size list, how many nodes are inside it. We take a look at this again. We have the idea that the array node itself is what is the list itself is composed of. There is a selection of them every time we add a new object to the list. There's another array node that is added to it as well with a next pointer that links it inside to where it's going to be pointing to. We also have the idea that with a list, it is resizable. Unlike an array where it is a static size, the list itself can be resized. We can add and remove components to this as needed. And we'll take a look at how that's structured and what it involves as we go through this next set of steps. First thing we want to look at now is the idea of the head. The head is that pointer that refers to the beginning of the list. It is just an array node pointer that we'll be using. And we have to update that pointer if we make any changes that affect the head of the list itself. So if we call add to front or add at index and pass it 0, that head address will need to be moved to reflect the new node that it's being pointing to. However, if we make any other changes to our list, whether we're affecting interior of the list or the tail itself, there doesn't have to be any changes made to the head because the head, again, just simply refers to the front of the list. And it's great for the idea when we have to traverse it. This is where we set our current iterator to, and we have to iterate over it. And we're going to go ahead and use that all the time, especially as we see what it takes to actually go through and manipulate the list here in just a minute. Now, on a singly linked list, the end node doesn't provide a lot of actual work duty. Rather, it simply just says, oh, here's where the end is. And it's great for the idea of adding to the end. We can use that to simply just add to the end immediately because we have that immediate reference. We don't have to iterate over the list itself, but rather we can simply move to that point specifically and then add at that point. Now, if we do use that feature to add to the end or add an index of size -1, we do have to make sure that we have dealing with that where we have to actually update where the end points to. But when we add at any other point, there's no other impact to the end because of the fact that when we're using a linked list in C++ and other languages as well, that the actual nodes themselves within that don't change. It's simply the memory pointers that go through it. So even if we continually adding right before end, the end pointer will still stay at that same spot because no matter how many nodes we add up until that point, it is still referring to that end location. And the constructor in our list is a lot simpler than we saw when we were looking at the constructor for the array. The constructor in the array has to build the entire structure, build all the links to all the nodes, and make sure they're all properly connected. However, when we're doing the constructor for our list, all we simply have to do is initialize some data members to basically a null value. Those are for the head and the end, because when we first create our list, they don't point to anything. And finally, our size is set to 0, because when we first make our list, nothing is in it. We have to actually add components to our list first before we can actually use it and do things with it. So the constructor is very simple. It's simply just 3 lines of code that initializes those values to null pointer and 0. When we look at the destructor, however, the destructor of our list has a little bit more work that needs to be happening. Obviously, we have to create a pointer reference so we can start pointing off at the next of head. And what we will do is we're going to loop over the entire structure of the list, and we'll continually remove head and move head then to what current.next is listed as. So again, we point it to the head's next. We set the head node. We delete that node object. We move the head pointer to point to current, and then set current then to be current.getNext. And repeat that until our next is equal to null, and then we simply delete head, going through and removing all of the memory allocations that have been attached to that list. Now, when adding a node, we have a sequence of events we have to actually deal with. So we've got a little bit of detail we have to go through here. Basically, with the idea of add a node as the add at index is the main thing we're talking about. We have some special looks at we're talking about the add at index. We have some special method information we have to deal with when we're doing the add at front or add at in. And those will actually say for you guys to implement on your own, but the idea is that you have to make sure you deal with the actual head pointer. When we're adding a node, this is like basically the framework for the add at index method. Now, when we're dealing with the idea of the add at front or add at end, there's some special information you have to do, and we'll talk about that in just a few slides as how we can address that. But basically, we're always adding at an index regardless of the position that we're dealing with. We do have to make a check when we're actually doing add at index. We have to make sure that the index itself is greater than or equal to 0, so we can actually put it into that point, and it's less than or equal to size, because we can add it the one that's after the current end at that point. And that's the only time we can actually go to equal size when we're dealing with this, because when we're adding that size, we're actually adding to the end again. So when we do the idea of this, we want to make sure we have the references to the previous and next nodes. We have to keep track of that. So we have to make a reference variable inside our method that can hold those things. So we'll have to have a couple pointers. I usually call them previous and next. When we continue adding the node, we have to make sure we create that node that has that associated value. So we'll create that node object. And then what we will need to do is we need to set the previous is next to that new node. So we have that, the next is now pointing to that new node. And because we've already assigned the previous is next to a temporary variable, we then will set the new nodes next to what was that previous is next. So we don't lose that information. We can simply just insert this new node into that original spot and then continue with the list. We do have to also make sure that we increment the size property. We want to make sure that the size of our list accurately reflects what is inside it. So when we call add at index or add at front or otherwise, we need to make sure that we actually properly increment the size of the node. We need to make sure we properly increment the size of the list. This can be done either with a method or by simply doing ++. Now, like I was saying, we have a couple special cases that we need to do when we're actually adding at a specific spot. And so if the index is equal to 0, we want to make sure that we are adding to the front. And if index is equal to size minus 1 or size, we have to make sure we have the call to add to end so we can actually replace what is there and have that link so we have that information there. Because when we're dealing with those two special things, the head and end pointer, we have to make sure we keep track of them throughout the project. And so this way we can also talk about the idea of making sure those are taken care of. And so these will have a little bit of separate instructions because obviously the head node doesn't have a previous and the tell or end node doesn't have a next. It simply points to null. And so you have to make sure you deal with those two special cases appropriately. Removing a node is a little bit more work. When we're removing a node, it's the same idea of removing from the index. We're passing it some index. However, when we're removing a node, we have to do a couple extra checks on that because removing a node requires a little bit more information from us as the user or the programmer. The first thing we have to do is we have to first check that the size itself of our list is greater than 0. You can't remove something that the list itself doesn't exist, so we have to check that immediately. And we usually use an assert statement for that. Then we have to check, after doing that, we have to also check to make sure that the index itself is not less than 0, as well as the index itself is less than size. You can't remove things that are outside of bounds. And that bounds check is always a big part of what we're doing when we're dealing with data structures. Now when we're doing the removal, we also have to make sure we have 3 different pointer references that we create as part of that method. References for previous, the new next, and what we're going to be deleting. So we want to have to actually keep track of those 3 different things we're going to be using with this. And then the best thing to do is create a loop and go over and find the actual nodes that were attached to those ideas of the previous, new next, and to delete based on that index itself. And so we'd assign the nodes to the reference of the node that is at index minus 1 will be assigned to previous, the index at index plus 1 will be assigned to new next, and the to delete would be one is at an index. We continue on with this and we take the idea of we assign the variable, we assign the value of what is stored inside the to delete node. Because when we delete a node, we want to make sure we retrieve the value from that node. And so in order to do that, we have to make sure we put it inside a temporary variable, and that's going to be of some type. And then we save that in there immediately so we have access to that variable so we can return it at the end of the method. After we've retrieved the value from that to delete node, we need to make sure we delete that node that we're pointing to. That node needs to be removed from memory, and so we have to make sure we call delete on that. Again, we then set the previous is next reference to the new next pointer. We just simply call that new previous.set next and attach it to the address we have for the new next, and then we have that information ready to go, and it immediately makes it so that the previous next immediately skips past what was in delete me or to delete and goes directly to the new next. When we remove a node, we want to also make sure that we update the size property, and because of this is a great idea that we want to again look at the idea that if we are using the remove at index, we specifically go through and immediately make that change. And so if we have the idea of we're using the remove from front or remove from end, we have to make sure that we don't remove the size from that inappropriately. We also have to make sure at the very last line of our code, because it's a return type method, that we return the value that was stored inside that to delete pointer. And so we have a reference to that node and we can return that value that was stored inside it. Again, just like we saw with the adding, we have special cases we have to deal with for the indices of 0 and size minus 1. When we're removing from the head or from the end, we have to make sure that we update those 2 important pointers appropriately. Otherwise, we would run into a lot of null pointer exceptions and we're going to see our program crash and burn. And so we want to make sure we have a couple separate if tests to make sure that the parameter is dealt with that. I recommend doing those at the very front of the method so you can have that immediately dealt with before you actually start doing any other parts of the remove method. And again, we want to make sure we have the remove front, remove last for these cases because we have the idea of code reuse. When we have these already existing methods that do the work we need them to do, it's really the best idea to make sure that we call those methods rather than duplicating the same code over and over again. We'll see this when we're looking at the AP exam. One of the things that's most often penalized is when you overwrite an existing method or method that's been given earlier. By overwriting that method that was already given to you, you usually docked a point for that. And in general, in business practices with code, we want to make sure that we don't overdo the work we have. We don't need to add extra work to our code. We want to be the good kind of lazy and do the kind of code that works well and doesn't replicate itself repeatedly. Now, moving past the idea of add and remove, we have the more often called method of get. Get is how we retrieve the value that's stored inside our specific index. We have to assert that the index itself is within bounds. So again, we always have to make sure that assert index, check to make sure it's in bounds, check to make sure there is a size, and we're good to go with that. We simply create a pointer and set it to head. I usually call it current, and we iterate over each node until we we iterate over each node in the list until we reach the parameter specified by index, getting us to that individual pointer, and return the associated value from that node. Very much just a simple loop method with a simple if test. Really easy to do, and we can get that done. The set method works just like it did inside the CTEC array. When we're dealing with the idea of the set, we were replacing the value that is at that current spot. And so first, again, we have to make sure that we assert that the index that we're passing it is in bounds. We then create, again, a pointer to that node. We iterate over the list until we reach that index. And then we need to make sure that we replace the value with the one that has been passed to it and return the original value. So again, you want to make sure that you create a temp variable that can hold that original value so it can be returned and be consumed if needed. Oftentimes when we're doing this set, we're simply replacing a value and we don't actually pay attention to the original value that was in there, but we have to make sure that we give that option to the other programmers to use it if they need to. If there's any further questions, please feel free to take a look at the other notes attached to this, looking at the data structures videos inside that YouTube channel. Thanks and have a great day.